Hello everyone and welcome to yet another math video. In this video I want to talk all about functions. First I'm going to lead with the graphs, and if you're in my college algebra courses, this actually relates to week 7 stuff. Sorry, not sorry. I wanted to start with the visual so it made sense when we started looking at the tables, maps and set of ordered pairs and function equations. You have an idea of what each thing looks like. So when I look at some graphs, I'm going to look at the domain and range of graphs, the maximum and minimum of graphs, the intercepts of the graphs, evaluating graphs, where a graph is increasing, decreasing, or constant, positive and negative, and finally, is it a function? Does the graph represent some kind of function? Now, with the second topic in this video being tables, maps, aka mapping diagrams, and sets of ordered pairs, we're only going to look at a few of these things, namely the domain and range, and whether or not the table, map, or set of ordered pairs is a function, and finally, evaluating. We'll evaluate some tables. Finally, the function equations. We'll do a little bit more with it. We'll go ahead and take a look at the domain and range and evaluating again, as well as whether or not it is a function. And finally, we will take a look where the function equations have their intercepts. Let's get into it. Before I get into all of the graphs and details of all of that and tables and whatnot, I need to go over some definitions. And the definitions you can see here, I'm going to go over relations, domains, range, and function. So the domain is the set of all allowable x values for a relation, and the range is the set of all y values for a relation. And in order to understand what these are, you should understand what a relation is. A relation is a set of ordered pairs x comma y. Now there are some relations that have a property that make them functions, and that function is each x value of the relation is only paired up with exactly one y value, where that is a super mathy definition. The non-mathy way that students remember is a function has no repeating x values. And there are specific ways to check for that in terms of a graph being a vertical line test. If you can draw a vertical line through a graph and it touches the graph more than once, then it's not a function. If you can draw vertical lines through the graph everywhere and all of the vertical lines only touch the graph once, then it's a function. As far as for a set of ordered pairs, you just check the x values to see if there are any repeating x values. If there is, then it's not a function. If there are no repeating x values, then it is a function. And finally, there are some special things just pertaining to college algebra for the equation version of a function having no repeating x values. And I'll get into that when I need to get into that. Let's take a look at some graphs. As promised, here is a graph. Now I want to point something out here very quickly is when I refer to the graph, I am referring to this blue plot here on the coordinate plane. The red axis and the y-axis, the x and y axis, I don't refer to those as the graph. I am simply referring to the blue ink here. The first thing we normally ask to do as a professor is, hey, does this graph represent a function? So what I have off screen here is a vertical line. We will use the vertical line test to check whether this is a function. So I can leave that vertical line right there. As long as I can find one vertical line that intersects or crosses the graph more than once, it crosses here and here, then that graph does not represent a function. So that actually limits us on a few things we can describe about this graph. But everything here we can describe even though it's still not a function. So let me get this line out of here. All right, the first of which is we can describe the maximum of this function. Now the maximum just means the highest point. The maximum is a y value. So all we have to do is find out the highest point on this graph. In fact, it's all of this. We just need to know what is the y value of any of these points. So we can just count up from the origin, 1, 2, 3, 4. The maximum here is 4. And very similarly, the minimum is the lowest point on the graph. So way down here, this blue lines, they don't go any lower than this point right here. So here we have a minimum, and the minimum we can just count down until we get to the same layer or level as this point. 1, 2, 3, 4, 5 down. That means the minimum will be -5. Now what's really interesting about this is that we can use the maximum and minimum, if you can find them, to describe the range. Remember, the range from the last slide is all of the possible y values that this graph covers. Well, this graph covers y values from -5 all the way up to 4. And you can do that because that will be the range, because you can move from -5 all the way up to 4 without lifting your pencil or whatever writing utensil you use. But this brings up a really nice point here. In interval notation, it's like this. The range will go from the minimum to the maximum, -5 to 4. Nice. Now the domain is kind of like the range, where we have to go from the minimum to the maximum. In the y values, minimum would be down and maximum would be up, but in the x direction, just like the old number line. So the minimum x value here would be to the left. Minimum means smallest, smaller numbers are to the left. So here's the leftmost side of this graph. I think this x value here is -3. And how far right does this graph go? Well, it looks like this is the rightmost point of the graph. If we count over 1, 2, 3, 4, 5. So the rightmost point here, or the rightmost side of this graph, is 5. So it's like the range, but you're doing it from left to right. Now to make that a little more general, when you're finding domain and range both, you go from negative side to the positive side. And one thing back here with the max and the min, these are y values only. All right, from there we can move on to evaluating a graph. And that's what these are down here, evaluating a graph. Now before I get too deep into this, I want to have a few notes here. Those being, we're going to introduce a new notation being function notation. And what that does is it is going to more or less get rid of y's and introduce this new function notation. And you might take a minute to write this down. You say this f of x, f of x, and that's it. So as you can see, maybe you can see, in terms of graph, I think this is just a really fancy way to write an ordered pair. You can see the x is still here, the y is still there. So essentially, what this is doing is it is asking you to find a y value, right? F of x equals y. We don't know what this equals, paired up with the x value of 0. You can see there, this is an x value. There it is. So you can look at this graph and I say, well, maybe the x value, I can just start picking points. Let's pick this point right here. What's the x value of that ordered pair? Well, it's just -3, which means I don't want it. I'm looking for where an x value is 0. So I can keep picking random points like that point right there. This coordinate pair has an x value of 5. Again, not what I'm interested in. So you look around, you say, well, x value of 0 means you haven't moved left or right at all. And what that means is you're looking for this point right here. And so when you find a point on the graph with an x value of 0, the y value that is associated with it will be your answer. And you can see that down here, x comma y would be 0 comma 4. Yep, that is an ordered pair that's on the graph. But it's not the only one. If you look down here on the graph, this is another ordered pair that has an x value of 0. It just so happens that the y value this time is -4. And you need to list off every time that happens. So the answers here, we would have 2 different answers because there are 2 different points on the graph that have an x value of 0. And something very similar happens for the y values. I'm going to do this in, let's see, pink. So when the x value is 2, what are the y values that are paired up with that? Well, I see a point here, and I see a point here. So this would be 2 comma 4, and this would be 2, oh wow, I didn't pick those on purpose, I swear. So we have 2 points that have an x value of 2, so the y values of those 2 points are 4 and -4. Finally, intercepts. Intercepts are where a graph crosses an axis. So an x-intercept, we'll abbreviate xint, is where a graph will cross the x-axis. So you just go across the whole x-axis left to right, and you tell me where the graph crosses right there. What's the x-coordinate? 1 to -3 to the left. So -3 comma 0. You didn't move up or down, it's just right there. And if you keep traveling to the right, there's another x-intercept right here at 5 comma 0. Okay, and then the y-intercepts are where a graph crosses the y-axis, which we already found. So these would be 0 comma 4 and 0 comma -4. And yes, you need to list these out as ordered pairs as they are locations on the coordinate plane. Now, one final thing I want to point out here is the x-intercepts will always have a y-coordinate of 0, and y-intercepts will always have an x-coordinate of 0 every single time. And if you don't believe me, we sort of inadvertently proved it back here. An x-coordinate of 0 means you don't move left, you don't move right. Boom, there was one of them. Boom, there was the other, just like we had listed over here. Another example. The first thing you're asked to do this time, again, is tell whether or not the graph here represents a function. And so what I'm going to do is I'm going to bring that vertical line back and say, hey, look, we have this vertical line. If you stop this vertical line right here, it looks like it would be a graph because it only would be a function because it only crosses the graph once. You can't stop moving. You have to move all the way across. And if you do that, we only need one vertical line for it to not be a function. One vertical line to pass through the graph more than once. So if I stop the vertical line here, you can tell this is not a function. And it's even more apparent if I keep moving it along. Here, the vertical line crosses the graph 3 times. That's still more than once. So this is not a function. No. On to the max and min, and this is slightly different from the last example as well. Say the max. The max is the highest y value over here, and it looks like it might be 1, 2, 3, 4, because I made the graph stop there at 4. And I ask my classes, what direction is this arrow pointing? And a lot of students say, to the right, and they're correct. But in a 2-dimensional space with a y dimension added now, this arrow not only is pointing to the right, it is also pointing up. It doesn't look like it, but this graph will go up forever. And if a graph goes up forever, there is no maximum. It just keeps climbing and climbing and climbing. And the similar thing happens over here with the minimum. It's the lowest point, the lowest y, the smallest y value. This graph not only, or arrow, is not pointing left and going left forever, it is also going down forever. So this also has no minimum. And if there is no maximum and there is no minimum, and you have arrows pointing toward the maximum and toward the minimum, then your range is negative infinity to infinity. It's everything. It goes down forever, negative infinity. These are negative y values. It goes up forever, positive infinity. These are positive y values. Yeah, range, negative infinity to infinity. So the lowest point to highest point, range, left point to right point, domain. And you might argue, so you count over here, this is -7. But the arrow is pointing left, which means it goes forever left. So that means the smallest x value here is also negative infinity. And then it goes to the right forever. That means x values keep getting bigger and bigger and bigger forever. That will be a positive infinity. All right, just like the last example, we can evaluate the graph. So I could just start picking random points and hope I get an x value of 0. Or I can just find those x values of being 0 right here. This is 0, comma, -4. There's another one right here. This point is 0, comma, 0. And right here, this point is 0, comma, 2. So those will be those x values, or sorry, y values, 2, 0, and -4. Those will be your answers. There we go. As far as f of -4 is concerned, well, we have to go over to the -4. This is an x value, so we know we have to go over to -4, and this would be the point here. So all we have to do is identify the coordinates of that point, and we can move on. Let's see, this is -4, comma, 1, 2, 3, 4, 5, -5. All right, so we would only have one answer here, because if you look, when x equals -4, this is the only point on the graph that matches it, that x coordinate. Now the last one down here, you want to find an x so that f of x equals 2. Now from the last slide, this is f of x equals y. So this is a y value. Okay, so now we have to come along and find a y value of 2, like this point right here. So that means basically you want to go up to the 2 on the y-axis and see where the graph crosses that. All of these points on this horizontal line have a y value of 2. Thankfully, we already have that point listed right there. So the answer here would be x equals 0. And finally, for the intercepts, we can go through, we've already identified the y-intercepts where the graph crosses the y-axis. And I promise that's not going to happen every single time for you. But we've already identified those points, so why don't I go ahead and say the y-intercepts are 0, 2, 0, 0, and 0, negative 4. And just as a reminder, when you're finding the y-intercepts, the x-intercepts will be 0. Sorry, the x-coordinates of every y-intercept will be 0. Now, there's a bit of an odd thing that happens here because the next part is finding x-intercepts. And remember, x-intercepts happen when the y-coordinate is 0. So we have this point here with the y-coordinate 0. This is also an x-intercept. Let me do this. There we go. 0, 0. And as a reminder here, the y-coordinate will be 0 when you're writing down your x-intercepts or finding your x-intercepts. So this leads to a nice little discovery here. The point at the origin, 0, 0, can both simultaneously be a y-intercept and an x-intercept. And that will be the only point that can be both at the same time because it is on the x-axis and the y-axis at the same time. Last example for graphs. All right. First question, does this graph represent a function? Well, I'm going to bring in my handy dandy vertical line again, and I have to move it left to right. So it only is ever crossing the graph one time so far, and I want to make sure it does it the entire way across. Yep, it's only crossing once, All right. This one is, in fact, a function. Hooray! That makes me happy. First graph that represents a function for this video. We can find a max, so let's go ahead and take a look at that. Is there a highest point? Yep, let's check over here real quick. Does any of this go above this point? No, all right. So the highest point here is 1, 2, 3, 4, 5, 6, 7. So yes, there is a max and it is 7. How about a minimum? Is there a minimum here? What's the lowest? Oh, I see an arrow. Okay, an arrow pointing down. That's very obviously pointing down. There's no min here. So the range this time will look a little different. It'll be negative infinity because there is no minimum. It's forever down. And the maximum is 7, and there will be a square bracket on it because that is the highest point. All right, the domain here, again, starts at negative x values. Not only is this arrow pointing down, it's also pointing left. I tried to make that apparent by making this graph curve out to the left a little bit. So left forever for the domain would be negative infinity. But as we trace along it, how far does it go to the right? Does it come out all the way over here? No, it looks like it stops right here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Looks like it stops way out there at 10 with a square bracket on it. Now there are domains and ranges that will end up having parentheses around the numbers. I have a very small example on the next slide for that. As for following the trend here, we can find some function values. We can evaluate a function. So f of negative 2 would be here, right? Negative 2, that's the x value. We can follow it up to this point. What are the coordinates of that point? Well, negative 2, 7. Let's do this, negative 2, 7. That's that point right there. That means the y value that's paired up with the x value of negative 2 is 7. Now what's really interesting about this is once you have a function, you really get a sense for the definition of a function I said earlier in the video. Each x value will only pair up with one y value. I could ask you, what is f of negative 4, f of negative 3, f of negative 2, f of 0? All these I could ask you for as far as x is concerned, and I would only get back one value of y for that x. If you go back and look at the last two examples, there were multiple values of y for some x's that I pointed out. All right, again, we can look here. Find x, so f of x equals 0. Well, this is a y value this time, so we're trying to find a y value of 0 somewhere on this axis. So take a look, there it is, the y value. We don't go up or down anywhere. So let's look left of that point, and you can see that this point will have a y value of 0. So this y value of 0 is paired up with an x value of -4. So we know x will be -4, but not only do you have to look left for this, you also have to look right. So when you find that y value of 0 on the y-axis, yes, there's an ordered pair over here with a y coordinate of 0, but there's also one over here with a y coordinate of 0. So let's say 1, 0. So that means x could either be -4 or 1. Now, I just got done saying, hey, every x value is only paired up with one y value. Why did we get two answers here? Think about this. This x value can be substituted in here for x. So -4, f of -4 equals 0. -4 is paired up with 0 only. No other y values listed here. -4 x value only has one y partner. And the same thing can be said about 1. If you put 1 in for x, that's saying f of 1 is 0, so that x value of 1 is paired up with a y value of 0. Are there any other y values paired up with that? Find an x value of 1. Any other y values? Nope, just this one. All right, so find x, so f of x equals 6. So again, this is a y value. Find 6 on the y-axis, look left. Looks like there are a couple points over here that have a y value of +6. Look right. Does the graph on the right side over here have any y values of +6? Doesn't look that way. All right, so that means x here would be -1 and -3. And since this is a function, you can now introduce increasing, decreasing, and constant. And the easiest way to think about where a function is increasing, decreasing, or constant is to think of them as mini domains. So before we even get into what are the answers here, let's just take a look at how you can identify where a function is increasing, decreasing, or constant. Keeping in mind that these represent many domains, we will have an interval, okay? From there, keeping in mind that these are many domains, and domains are found moving left to right across the graph, that's what we're gonna do. We're gonna start as far left as we can, and I'm just gonna trace the graph. So increasing, decreasing, or constant is telling you which way are you tracing. Are you tracing up? Are you tracing down? Or are you tracing flat? All right, so starting here, this is as far left as my graph goes. Am I going up or down? Well, I'm going up, so this is increasing. And right here, the graph stops increasing. And after this point, it starts decreasing. So, what are you going to remember? We have to move left to right. There will be intervals because these are many domains. But which letter does domain represent? Well, you only have two choices, x and y. Domain represents x. So what's going to happen is when you get to a point in the graph where it stops doing one thing and starts doing another, you will draw a line to the x-axis like this. And over here, I'm going to say I for increasing. It's also important to note, where does this line hit the x-axis? I'm going to say -2. So let's keep traveling. From here, it starts decreasing, 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 and it stops right here. So what I'm going to do is I'm going to, again, draw that line to the x-axis, even though it's on the x-axis. Put your line in there. Mark it. It's decreasing here. Where does it stop decreasing? Right here at x equals 1. Keep tracing. It stops decreasing. It's doing something else on the right side. So this is increasing, increasing, increasing until here. Boop. Draw a line down to the x-axis. This is increasing. And then after this, it's flat, flat, flat. So this is constant, and it stops being flat right there. So how do you do this? You write down a few intervals. All right, so you do it like little domains. How far left does this point? Well, forever left. When does it stop increasing? Well, -2. When you're doing intervals for increasing, decreasing, and constant, always use parentheses. Okie dokie. Now, let's take a look at where it's decreasing. Where does it start decreasing? Oh, over here on the left side, -2. Where does it stop decreasing? Oh, over here on the right side, 1. So you can just put -2, 1. How about the next portion of the graph? What's happening? It's increasing here. Oh, it's increasing again. We already have an increasing interval, so let's just continue that line. It's increasing from 1 out to 6. I know I didn't mark that up here. Let me mark it. 6, 10. There we go. But this presents us with now 2 intervals for the same idea. You have to join those intervals together with a union, and it is just a big capital U like that. Lastly, we have, where is the function constant? It starts at 6 moving left to right, ends at 10. So from 6 to 10. And that's it. That's how you can find out where things are increasing, decreasing, or constant. Only if the graph represents a function. Before I get into some domains with parentheses around the numbers, what I want to quickly do is go over the idea of where a graph is positive, negative, or equal to 0. Now, you can see down here, positive, negative, equals 0. These all represent or describe y values again. So over here on the right of this graph, a y value will equal 0 if it's on the x-axis. And I hope that makes sense and that lines up with what we talked about with what x-intercepts are. X-intercepts have to be on the x-axis, so the y-coordinates have to be 0. And then any point that is above the x-axis will have a positive y value. I'll prove it to you, watch, 1. Yay! And any part of the graph that is below the x-axis will have a negative y value. Watch this, -1. And they all keep getting more negative from there. So the easiest thing for you to do to identify where's a graph positive, negative, or 0 is to do something similar to where it's increasing or decreasing, but where it stops increasing and starts decreasing is not going to be where we cut it off this time. What we're going to do is we're going to cut it off where the graph equals 0. And so that would be any point that is on the x-axis, like this point right here or this point right here, and those are the only 2. So we can quickly knock those out. This is an x value of 1 and an x value of -4. So the graph equals 0 at 1 and -4. You also, just like with increasing, decreasing, and constant, can think of these as mini domains. So we are going from left to right. So as I start here, I'm just going to label them now really quickly. And really all we have to do is figure out, is this above or below the x-axis? Well, it's below, so I'm going to go ahead and mark this with a negative. Right here, it changes from being negative to positive, right? This is above the x-axis, so we'll go ahead and call this positive. But what's really kind of funny here is this point right here. It comes down and touches the x-axis, and then it goes positive again. That will create a separate interval. Okay, I think we can write these intervals out now. Where's the graph positive? Oh, we'll just go left to right. This is negative. So starting at, left forever, this would be negative infinity. When does it stop being negative? Right there. Boop, at -4. This one you have to use parentheses. What happens after this between -4 and 1? Oh, it's positive. So why don't we just write that interval here? Let's do this there. -4 to 1. But we have another interval here, right? From 1 all the way over to 10, where the graph stops. This is also positive. So 1 to 10. Oh, we've got two intervals here. Join them together with a union. And there are your answers for where the graph is positive or negative. And I'm going to end this video here. This has already been way too long of a video. I'll have another one up for y'all shortly about, the rest of the content of this video being tables and sets of ordered pairs and mapping diagrams and function equations. See you next time.